Yeah, should be okay. Okay, so welcome everyone to the IPhT Colloquium. Today we are very happy to have Matt HEADRICK from Brandeis University, and he is also he's visiting for a year at IHES, so it's very close to here, so if you want to talk to him, I guess it will be possible. And today the talk will be about black holes, quantum entanglement, and the geometry of space-time.
Okay, thank you for coming. Thank you for inviting me. Today I'm going to talk about a subject that I started working on almost 20 years ago, and I've been working on more or less continuously since then. I kind of fell in love with it when I started because I just found it, I found the connections between quantum mechanics and space-time geometry incredibly compelling. So that's the story I'm going to try to tell today. It's a story about quantum gravity, which came out of work on quantum gravity, work on string theory, and so on, but which led to basically a new perspective on problems in quantum gravity. So traditionally, quantum gravity as studied by string theorists was in the tradition of high-energy physicists who were studying things like scattering amplitudes. And around 25 years ago, we discovered, and of course that continues to be a very productive way of studying quantum gravity, but we discovered another way, which is to focus on the quantum part and think about the quantum information contained in quantum gravity. And so that's what I'm going to try to touch on today. And of course I'll only, because it's a colloquium, I'll only be able to describe a very narrow path through this large area. And of course, you're welcome to interrupt me with questions at any time, or corrections if I say something wrong. Okay, so I'm going to start with my favorite formula in physics, which was discovered over 50 years ago now, which is the Bekenstein-Hawking formula. It tells you the entropy of a black hole in terms of the area of the event horizon. Just so we get a sense of what happens when you plug in numbers in this formula, it predicts, not only does it tell you that black holes have an entropy, that was of course the major discovery of Bekenstein and Hawking, but just for some perspective, they have a ginormous entropy. So if you take a garden variety of black hole of the kind which is now observed routinely by LIGO, which is in the 10 to 40 solar mass range, you get a ridiculously large entropy. And if you take a supermassive black hole like this one, if I figure out how to use this pointer, this one, which was imaged by Event Horizon Telescope, that has an entropy which exceeds the entropy of all of the matter in the universe by a good factor. This is, of course, so this is the entropy of the universe, obviously not including the black holes. So this is the entropy of the matter in the universe, which is mostly the entropy of the CMB photons. Every time LIGO observes two black holes merging, there is an increase in entropy. That's an irreversible process that produces on the order of 10 to the 80 units of entropy, which is quite a bit more than the entropy of all of the matter in the galaxy that it's in. So by far, almost all of the entropy in the universe is in black holes, by far. And of course, the reason why you get such large numbers is because gravity is very weak and h bar is very small on astrophysical scale. So compared to the things like the masses that come into this formula. Now, so that's sort of what happens when you apply this formula in the real world. That's the last I'm going to mention of any real world applications of quantum gravity or black hole entropy. Let's look at this now from a theorist's viewpoint. And from a theorist's viewpoint, what's amazing about this formula, what's beautiful, is that it has so many different constants of nature. So it contains within it the speed of light, that's perhaps no surprise, and Newton's constant because we're talking about gravity, black holes, but also h bar, which means it's a quantum mechanical formula, and Boltzmann's constant, which means it's actually a statistical mechanical formula. In other words, the presence of Boltzmann's constant in this formula tells you immediately that this formula is about microstate counting. It's not a thermodynamic formula, it's a stat-mech form. It's stat-mech formulas that have Boltzmann's constant in them. And that's already a huge piece of information that you get just from the form of this formula, actually. Unfortunately, I don't have time to go through how they figured out this beautiful formula. That's a lovely story. But when you do the derivation, you do end up with this Boltzmann's constant out front. Now, as a theorist, and you guys are, if I understand correctly, mostly theorists, you know that in practice we often set fundamental constants to 1 when it's convenient, because otherwise it's annoying to have them hanging around in formulas. So when you're doing stat-mech, you would often set Boltzmann's constant to 1, set the speed of light to 1. When you're doing like quantum field theory, set h bar to 1. Okay, so I'm not going to include these. I'm going to have formulas like this in the rest of the talk, and I'm not going to write the speed of light, g, or h bar. Oh, one other thing I want to say about this, actually, is that in the rest of the talk, because I'm a theorist, I'm not necessarily going to be in 3+1 dimensions. And so you might want to know whether this formula, so the first statement is there are black holes in other numbers of dimensions, in lower and higher dimensions. And the second is that this formula is still valid in different numbers of dimensions. When you do the dimensional analysis, you see that actually it's unchanged in other dimensions except for the power of the speed of light, which depends on the dimension. And in particular, if we get rid of the speed of light here, which is definitely the most annoying constant to keep hanging around when you're trying to do some relativity, so if we just set that to 1, then we get this clean formula with the Boltzmann's constant and g and h bar in the denominator. And I just want to say this very important fact, this will be crucial actually for the whole rest of the talk, is that the product GH bar has the units of area in any number of dimension. And by area, so now I have to tell you what I mean by area if I'm changing the dimension. What I mean by area is 1 dimension less than the number of dimensions of space. Because I'm comparing it to what? I'm comparing it to an event horizon area, and an event horizon is, you can think of it as like a membrane that separates the outside from the inside of the black hole. So that is codimension 1 in terms of space. So Newton's constant times h bar in any number of dimensions has the units of area in the sense of a surface that has 1 dimension less than the number of dimensions of space. Okay, so now there's this funny question. I know theorists sometimes like to argue, and I sometimes enjoy arguing about whether or not to set certain constants to 1 or what it means when you set constants to 1. It's a fun philosophical question. And so you can ask the same question here. I mean, I just went ahead and set these to 1. And the reason, of course, is that what they are fundamentally is conversion factors. You know, space and time are equivalent, so you have a conversion factor between length and time, conversion factor between momentum and length for h bar and so on, between energy and temperature for Boltzmann's constant. So what about Newton's constant? Should we set it to 1 or not? And I think it's not a completely obvious question, because on the one hand, you can think of it as a conversion factor. When you do general relativity, it's the conversion factor between mass and length. So the Schwarzschild radius is 2 gm, twice Newton's constant times the mass. So it's a conversion factor between mass and length. On the other hand, it refers to a force. It's the strength of a force, and that's a coupling constant, and we don't normally set those to 1 in physics. I mean, you can set the charge of the electron to 1, but when you're doing QED, you normally don't set the charge of the electron to 1. You instead have the coupling constant, alpha. So maybe I'll ask your opinion, ask the audience, should we set Newton's constant to 1? So we'll take a vote. Don't worry, you don't have to vote. If you think we should set Newton's constant to 1 and just be done with it and simplify this formula, raise your hand. If you think we shouldn't, raise your hand. Nice. Okay, Yusuf, you'll have to explain to them why they're all wrong. Okay, so of course, I mean, whether you should or you shouldn't, you certainly can. Mathematically, it's allowed, and that gives you the famous Planck constant, Planck units, which are, of course, when it comes to things like length and time, are very small, which is why these entropies are very large, and in terms of energy, at least by particle physics standards, they're very large, so 10 to the 16 TeV. And so that's what leads to this basic problem with quantizing gravity, which is that if you think about quantum fluctuations going back, general relativity is a theory where space-time geometry is dynamical, and therefore when you combine it with quantum mechanics, you get zero-point fluctuations in the geometry of space-time. You can ask how big those are. Those will depend on the scale. You can do a quick dimensional analysis, and you see that the effective coupling at a given length or energy is g times e squared, or g over L squared. And so what happens is that as the length goes smaller and smaller, closer to the Planck length, the fluctuations in space-time geometry grow out of control. So here's the coupling constant versus the length. And so here's the Planck scale. So down here, you've completely lost control in this theory where we've naively combined quantum mechanics with gravity. And here's where we are experimentally in terms of probing the structure of space-time directly. So the probes, if you ask, what is the length scale at which we know the structure of space-time, the smallest length scale? I mean, we know that on human scales, it's a nice, smooth, four-dimensional manifold, continuous manifold, and that goes down to 10 to the minus 18 or 10 to the minus 19 meters where it's been directly probed. Below that, we have no idea, basically, what the structure of space-time is, whether it continues to be smooth, whether it continues to be four-dimensional, whether there's some other structures at that length scale, okay? And so, I mean, as you no doubt heard, in string theory, that this problem is overcome, but I mean, I'll say in a second, but let me just say that, I mean, of course, there are other theories of quantum gravity besides string theory. I mean, none of them really work, but they are, people write papers and so on them. There's like causal dynamical triangulation, loop quantum gravity, and all of these things. And just philosophically, what they do is they fix the problem here. So they say there's a problem here, we're going to fix the problem here. And so it's kind of like a procrastinator who waits until the deadline to do the assignment, right? You wait until it's an emergency, and then you try to fix it. So that's not really the philosophy in string theory, where you introduce a new length scale, and that length scale is a fundamental length scale. It's defined by the tension of a string, which is a new fundamental constant. So the tension of a string, or equivalently, so because the string has a certain tension, the typical size of a string is 1 over the square root of that tension, and that's the string length. So you can think of either of these as being a fundamental constant. Now, of course, assuming string theory is a correct theory, we don't know what the string length is. So it's an unknown constant, but we know that it's less than 10 to the minus 18 meters because we've directly done experiments there. And we know that it's more than 10 to the minus 35 meters because by that time you've already lost control. So it's somewhere in that range. That's a pretty big range, obviously. And the point is that below the string scale, LS, space-time is not a smooth four-dimensional continuum anymore. It's more complicated. It's something that I'm not going to explain, but it's basically a new structure takes over that essentially deletes. So there's, in some sense, nothing going on below the string length. The string length is kind of the smallest distance you can probe. And so the whole issue never arises. There's no space-time foam. There's nothing that happens at the Planck length. So in fact, I mean, you may have heard that something special happens at the Planck length. Actually, we have no evidence that something special happens at the Planck length. We don't know anything about what happens at the Planck length or whether there is even a Planck length. So in string theory, the Planck length has no special meaning whatsoever. And the fundamental constant is not Newton's constant or the Planck length, but it's the string length or the tension of a string. And then Newton's constant is some derived quantity which can be made dimensionless by combining Newton's constant with the string length. And it's some constant which is much smaller than 1, and that is what controls the separation between the string length and the Planck length. And so it's just some order, it's just some dimensionless constant, okay? And of course, we don't know what its value is or what even determines its value. But from this viewpoint, you should not set G Newton to 1. You should not set Newton's constant to 1 because you should set the string tension to 1. That's normally what's done in string theory textbooks. Okay, so we have this, but then we have this Bekenstein-Hawking formula, okay? So, and the Bekenstein-Hawking formula does not have the string length or the string tension in it. It has Newton's constant in it. And so can you reproduce Bekenstein-Hawking formula from string theory? And the answer is yes. In fact, the world experts are in the audience and at this institution, so I'm not going to talk about that. But the answer is yes. And you do a complicated calculation in which the coupling constant enters in just such a way that you reproduce Bekenstein-Hawking. So you end up with that for G just where you wanted it to be. Okay? And the calculation is done by a literal counting of the number of microstates and then taking the logarithm as Boltzmann instructed us to do. So you do a complicated calculation, you get a simple result where Newton's constant actually reappears. But the thing is that, and there's many, in string theory, it's a very rich theory. You have different numbers of dimensions. You have all kinds of different objects, D-branes, and so on. So there's many different kinds of black holes in string theory. And they all obey this same formula, which is simple when you write it in terms of Newton's constant. Okay? And which is, universal not only for every string theory, but for every quantum theory of gravity. And so it's a little bit funny that you do this very complicated calculation and out falls this very simple answer. So a different viewpoint is that, in fact, it's this relation or something like it that you should take to be fundamental, okay? And this is encouraged by the fact that, like I said, G or GH bar has units of area in any number of dimensions, okay? So from this point of view, G is a conversion factor, not in the sense that I said before between length and mass, which is very special to 3 + 1 dimensions, but in the more general sense, a conversion factor between area and entropy, okay? And that actually, that is motivated by this observation that the Bekenstein-Hawking formula is simple for every quantum gravity theory and looks the same for every quantum gravity theory, okay? But it turns out to be vastly more general than that. That's what the rest of the talk is going to be. And this insight that perhaps you should think of gravity as derived from the area-entropy relation rather than the other way around was originally due to Jacobson. And he had a very clever derivation of the Einstein equation from essentially the Bekenstein-Hawking formula that I'm not going to tell you, but it's the fact that you can do that is already very, very intriguing. Okay? So if we wanted to think about the area-entropy relation as being fundamental, we have this problem that it's about black holes. And black holes are great. There are black holes in the world, but what about, I'm experiencing gravity right now on Earth, and it's not near a black hole, so it can't just be about black holes. So how could we make it more general, okay? So the answer to that is to think more generally about what entropy is, okay? And especially entropy in quantum mechanics. And so in classical mechanics, entropy is a measure of your ignorance, but in quantum mechanics, there's another source of entropy, which is entanglement. So let me just quickly review that. So a classic example of an entangled state of 2 spin 1/2 particles would be spin singlet state, which is up, down, minus, down, up. And that, of course, this is a pure state, has no entropy. But to know that it's pure, you need to have access to both particles. In other words, if you have many copies of this state and you do a lot of measurements and you want to know what state it is and is it pure or not, you would have to have access to both particles. If you just have access to the first particle, then as far as you're concerned, the state is mixed. That is 50% chance of spin up, 50% chance of spin down, and therefore it has an entropy of log 2. And this kind of entropy that you get from entanglement is called entanglement entropy, although it's a slightly misleading term in the sense that any entropy can be thought of as an entanglement entropy. In other words, you can go the other way. You could have started from something like this and said, it's my ignorance, I don't know whether the particles spin up or spin down, and then you could have formally added B and made a pure state out of the two. So you can remove you can turn any entropy into entanglement. Okay, so that's a simple example, but of course it's much more general. If you have any state on some multipartite quantum system, and you look at a part of it, so this is your state rho, the state for the part that you have access to is given by tracing out the rest of the system. So let's say this is your multipartite system, and here you only have access to A. Then the entropy of A is then the von Neumann entropy of that rho sub A. And that's, this is the quantity that the rest of the talk is going to be focused on. We'll refer to some, so I'll review some salient facts about entanglement entropies, but a couple of basic ones are subadditivity. So if you have two subsystems, part of some larger system, then you have subadditivity, and you can think about that in terms of the mutual information, which is the difference between the two sides, which is a measure of the amount of correlation between A and B. This correlation measured by the mutual information may be due to entanglement between A and B, as it would be in this case. So in this case, for example, what is the mutual information? Well, SA is log 2, SB is also log 2, SAB is 0. So you get 2 log 2, and that's due to entanglement. But it could also be due to correlation, classical correlation between A and B. That will also give you non-zero mutual information. And then there's a fancier version, which is strong subadditivity, which is this inequality, which is maybe a little bit hard to parse. But when you write it in terms of the mutual information, I hope you guys can see the bottom of the screen, you see what's going on is the statement that the mutual information between A and BC, the union of B and C, is at least as big as between A and B. In other words, A cannot have less correlation with BC than it does with B. So in other words, correlation is monotonic with respect to inclusion. And that's a fundamental fact about entanglement entropies. Okay, so we're going to do a little detour into entanglement entropies in quantum field theories, because quantum field theories are a rich source of, or if you want if you're a condensed matter person, many body systems of different kinds of entanglement, different phenomena that happen with entanglement. And I'm just going to scratch the surface here, but it helps to give intuition. And then when we come back to quantum gravity, it'll help to ground us. So this is some one-dimensional quantum field theory or many bodies. You can think of it as a spin chain if you want. And I've selected out some part of it. This is a two-dimensional one, and I've selected out some region. So there, of course, the entropy will depend on what state you're in, what theory, and so on. But there's some general phenomena that are good for building intuition. So one is that it is an ultraviolet divergent quantity because you have modes across the boundary of A. And so I'll use, so this dA is the boundary of A, which here would be this curve. And then the absolute value sign means the length or area of that. So it's, by dimensional analysis, it has to be that divided by your UV cutoff to the d minus 1. Little d is the number of dimensions of space. So that's just due to a pileup of modes near this dA, this entangling surface that separates A from its complement. If your theory is gapped or massive, then the entanglement kind of peters out past the correlation length or the Compton length, okay? And so that pileup kind of stops at some scale going toward the infrared. And so you get this kind of formula where you have a negative contribution proportion, which is dictated essentially by the correlation length. Or if you're in one dimension, the pileup gives you a log. And this is also a log, by the way, in one dimension. And this is not an exact formula. There's all kind of course, it depends on the details of your state. It depends on the details of your geometry and so on. This is just some patterns that you get. In a conformal theory, you have long-range entanglement. And so here it gets cut off not by the correlation length, because the correlation length is infinite, but by the size of your subsystem. So you have this formula that the entanglement entropy is proportional to the log of L over epsilon with a coefficient that is determined by the central charge of your CFT. Okay? And there are similar, more complicated formulas in higher dimensions. Then, of course, if you're at finite temperature, then you have an extensive thermal entropy, which also contributes. Sorry about that. So, for example, here you would have something which is just proportional to the area of this this region and times the entropy density. So little s would be just your entropy density at a temperature T. Okay. So we have a distinction here between this, which would be called volume law, and this kind of thing, or this kind of thing, which would be called area law. Okay, so that, of course, one could give a colloquium or a semester-long course on entanglement entropies in quantum field theories and all the things they reveal to us, but that's not the main point of this colloquium. I'm telling you these things because they're going to come back to us. So this slide doesn't seem to have too much to do with black holes, but actually it does. The reason is that actually we can, in certain quantum gravity theories, we can actually make a sharp connection between entanglement entropy and black hole entropy. Okay? So these aren't two distinct concepts. So in other words, we can think of black hole entropy as an entanglement entropy. And to do that in a well-controlled way, we need to basically, in some sense, get rid of the gravity, which seems like throwing away the baby with the bathwater. But we'll see that we'll have our cake and eat it too. Sorry for all the bad metaphors. By keeping the gravity and throwing it away at the same time. So to do that, we need to make a couple of adjustments to our quantum gravity theory to be able to pull off this trick of thinking of black hole entropy as entanglement entropy. So the first thing we need to do is we need to glue on a boundary to our space, okay? And this is where, to do that, you need to have a negative cosmological constant. In our universe, the cosmological constant is positive, but as a theorist, we can make the cosmological constant negative. In fact, it's easier to make it negative than positive in quantum theories of gravity. And when you have a negative, so you know that in our universe, with a positive cosmological constant, it's causing the universe's expansion to accelerate. With negative, it causes the expansion to decelerate and the universe to collapse. And then what you do to prevent that is you basically attach a boundary, like putting a drum head on, attaching a drum head to a drum. The drum head, the sheet is under tension. It wants to shrink, and you prevent it from shrinking, and you get this thing under tension. So you do the same thing with the universe. You just glue it to a boundary to prevent it from shrinking, and the space-time, the relevant space-time, if it means something to you, is anti-de Sitter space. If it doesn't, that's okay. We're not going to go into the specifics on that. But now we have a boundary, and something interesting happens. So here is my universe with quantum gravity in it, and it's got some gravitational waves and matter and whatever, and then it has a boundary, and there's some specific reflecting boundary conditions, so it makes a nice closed system. And that closed system turns out actually to be equivalent to a quantum field theory. Okay, so it ends up being, so the fact that my closed quantum gravity system is a quantum mechanical system, that's almost by definition. The fact that it is a local quantum field theory that lives on the boundary, that is not at all obvious, okay? So you're going to have to trust me on that. So there's a whole song and dance to explain why that's the case. So we have this equivalence between, which is called holographic, between a quantum gravity theory in some number of dimensions and a quantum field theory in one less dimension. Okay. And this is called holographic because you can think of the quantum gravity, going the other way. So the way I described it is we started with a quantum gravity theory, we attached a boundary, we got a quantum field theory, but you couldn't think of it the other way. You start with a quantum field theory, and then poof, a quantum gravity theory emerges, and that is the hologram. Okay? Now, this QFT you get is not just any old QFT. It is a complicated one. It's strongly coupled. It has a large number of degrees of freedom. Otherwise, you cannot get such a miracle to occur. And so it's this equivalence between the complicated theories with a large number of degrees of freedom and quantum gravity theories is what's called holographic dualities. Now, since I have a quantum gravity theory, I have black holes. Okay, and so every state, so it's an equivalent. So every state of the quantum gravity is equal to a state of the quantum field theory. A black hole has a temperature. That's what Hawking figured out. And so that means that a state that contains a black hole is a state of the QFT that's at a temperature. At least there's an issue about whether it's in equilibrium. So let me just put it this way. You can arrange it so that the black hole is in equilibrium. And when the black hole is at equilibrium, then the QFT is in equilibrium at some temperature. Okay? And essentially the physics of that, since we had a strongly coupled, often a gauge theory, the physics of that is that you are in a deconfined phase, meaning that you have a very, very large entropy density, and that's going to be the equivalent of the very large entropy that we have for our black hole that we already saw before. Okay? So that's fine. So so far there's no entanglement entropy in this. There's just a universe with a black hole in it, which is equivalent to a quantum field theory at some finite temperature in a deconfined plasma. But now I want to think about that black hole entropy in terms of entanglement entropy. And I can do that by taking my quantum field theory and thinking about its entropy as an entanglement entropy, which I do by adding a second system and reinterpreting my thermal entropy as entanglement entropy. So I now have a second quantum field theory, which is entangled with the first one, and that turns out to have a description as a second universe. So you can extend this. Actually, I didn't say it. I should have. Sorry. I should have said this is a picture of the space with a black hole. So we have the same boundary, and then this is the event horizon. So this is a fixed time snapshot. And this is the event horizon, and the event horizon is what gives us the entropy. So anyway, so now we turn it into an entanglement entropy by adding a second system, which is actually the same as the first system, a second copy of the first system. And now this entropy, which is a thermal entropy from the point of view of one subsystem, is an entanglement entropy from the point of view of the two. In other words, the two are in a pure state together.
Question?
Yeah.
Sorry. So when you say the black hole entropy is an entanglement entropy, you don't mean it's an entanglement entropy 3 + 1. You mean it's an entanglement entropy in the dual theory. Because usually when you go from one theory to the dual, you lose all completely track of what's entanglement. The changes of variable are not local usually.
Right. So it's true that you would. So this is an entanglement in the quantum field theory.
Yes, that's to the 3 + 1.
Yeah. Now, how you should think about that in terms of the dual, the gravity theory. So in the gravity theory, all I have, the fact that you can take a short shell black hole and extend it, add a second universe on the other side, and then you get this throat, is something that Einstein and Rosen discovered a long time ago. And obviously they were not thinking at all about entanglement, at least not in that paper. And so how you should think about that, so from the point of view of the quantum field theory, it's a very banal entanglement entropy that, you could always do. You give me any state, thermal or not, with some entropy, and I can purify by adding a second state and talk about it as if it was entanglement entropy. There's nothing special here. Then the dual of that is this Einstein-Rosen bridge. Is it entanglement entropy from that picture? That's not obvious, right? Okay, so yeah, that's right. Any other questions? Yeah.
So any state can be purified. So if you don't have a horizon, how do you make
Oh yeah, so then, if you don't have a horizon, then you end up with two copies that are not connected from each other. So for example, not to get too much into the details on this, but if you're at a low temperature, then the thermal equilibrium state will look kind of like this, with just a gas of gravitons and other massless particles bouncing around in this box. You can purify that, and then you'll get a second copy of the same box, and that gas of gravitons will be entangled with the gas of gravitons in the other box. But there'll be no geometrical connection. And in that kind of a state, the entropy is very low. So then you're in a confined phase of the gauge theory, which has a low entropy. And when you turn up the temperature, you pop into a deconfined phase, which has a very high entropy. So the low entropy is controlled by, low means it's not of order 1 over g, right? We saw when you have macroscopic horizon area divided by g, you get huge numbers, okay? So that versus low, order 1 or whatever, is when you're in the confined phase. Yeah, and you can study this in great detail. I mean, this phenomenon is, of course, the subject of many thousands of papers. Okay, but here we've discovered by this reasoning that a geometrical connection is related to an entanglement entropy. And how do we quantify that connection? Well, we already know the formula, because we know the Bekenstein-Hawking entropy is the same as the entanglement entropy, and that's given by the horizon over 4g. And the horizon is this minimal surface here. Okay, so we've learned from this thought experiment that the entanglement entropy in this situation is given in a very specific way by the area of the horizon. The horizon, what is the horizon in this picture? The horizon is the minimal surface separating these two asymptotic regions. Okay, so there's a minimal surface, there's a throat there, and Bekenstein and Hawking taught us that the area of that throat is an entanglement entropy. Okay? Yeah?
I have a naive question. Is this horizon or this bridge static, time invariant?
So it's not. It's not. So this is at a moment of time that happens to pass through. So what I'm calling the horizon is more properly called the bifurcation surface. So if you look at a moment of time that passes through this bifurcation surface, you get a pretty picture like that. If you then, as you evolve in time, this throat actually gets longer and it's dynamical. So this is actually, so I'm sweeping a ton of stuff under the rug. This is it's not just a moment in time, but I chose a very specific moment in time that is actually, has an extra symmetry. Yeah, this is the standard Schwarzschild solution. Just put in ADS. Yeah. So I mean, if you're, familiar with like Penrose diagrams, then this is my red surface, and this is what I drew the picture of. And if you go forward and backward in time, it's not static. Yeah. We'll come back to this issue of time, what to do with time evolution in a little bit. Any other questions? Okay, so we learned this lesson, which is that at least in this particular case, we have the area of a minimal surface giving me an entanglement entropy. And about 20 years ago, two physicists, Ryu and Takenagi, thought that was maybe a more general thing. So they extrapolated from this situation, which has a ton of symmetry, by the way. So the extrapolation they made was from a situation with symmetry to more general situations, and they said maybe the formula doesn't change. Okay, so they made that guess. And that gave us a formula which is called the Ryu-Takenagi formula. And it's an extrapolation of the formula I just told you. So the claim is that actually, if you have any holographic QFT, and you take any part of that QFT space, okay, so for example, here my QFT is one-dimensional, here it's two-dimensional, and here I've taken an interval, and here I've taken some region, okay? And in both cases, I'm assuming that it's holographic, so there's a dual description in terms of a quantum gravity theory. And they said, well, what you're supposed to do if you want to calculate the entropy of some region is you're supposed to find the minimal surface separating it from the complementary region on the boundary. So in here, in this, so I mean, this is obviously not a great drawing. There's some non-trivial metric, it's some curved space, and like you can think about it, for example, as like the Planck array disk as a simple example. And in the Planck array disk, if you look for a minimal surface connecting points on the boundary, a geodesic, so I'm using surface always to mean one dimension less. So here a surface is a curve, and in particular, since it's minimal, it's a geodesic. Okay, would be like an arc of a circle if it was the Planck array disk. But in any kind of geometry, you'll find some minimal surface or some geodesic connecting the endpoints of A. And here we have some, again, geometry, which is whatever it is. And in general, it has the property that as you go away from this boundary, the areas shrink, and therefore the surface, when you want to minimize a surface that is standing between A and its complement, so the surface standing between A and its complement has to be glued to the boundary on the boundary of A, okay? And then it's gonna want to hang down, not because of a gravitational potential, but because the areas are smaller down here than up here, okay? So you'll get some surface which hangs down, which separates A from its complement. And of course, the details will depend on the details of the geometry and so on. But they said, okay, this is the formula. It's just this simple. You find your minimal surface that does what it needs to do topologically, and you plug it into the Bekenstein-Hawking formula as if it was a horizon. These are not horizons, okay? But we're plugging them into the Bekenstein-Hawking formula as if they were horizons, okay? Another way to think about this is in terms of what we call bit threads. So these are Planck size curves that connect within the bulk A to its complement. And if you just pack as many as you can in, then, so because they have this Planckian thickness, eventually you can't pack any more in. And the maximum number you can pack in, you can prove via theorem, is actually equal to this. So that's just a different way. So you think about each of these threads as carrying one unit of entanglement, one Bell pair or EPR pair, of the shared entanglement between A and its complement. It's just an equivalent way to think about it. Subsequent developments showed that, so here I've got a region that lies between A and this minimal surface, okay? There will always be some region by this topological condition. There will always be some region lying between A and the minimal surface. And subsequent work showed that, by a lot of different people, which is why I didn't put the citations in, showed that actually that region is very special, okay? It is the dual of the QFT within the region A. So in other words, I can take my QFT, which is defined on the circle or on the plane, and then I restrict it to the region A. Keep the same state, okay? So now I have a QFT which is defined on some finite region, okay, in some state. And does that have a holographic dual? And the answer is yes, it does, and its holographic dual is that region which lies between A and gamma A, okay? I might use the term RT surface, so gamma A, I didn't write it. Gamma A is, we call it the RT surface, so for Ryu Takanagi. So if I say RT surface, I mean gamma A, okay? And what that means more precisely is that this subregion duality, so in other words, a duality between a subregion here and a subregion on the boundary and a subregion in the bulk, is that observables in the bulk, if an observable is inside this region, this bulk subregion, then that can be rewritten in terms of operators within this boundary subregion. So in general, the map between the bulk and the boundary is very non-trivial and non-local. It has to be because I've changed the number of dimensions. But it has this kind of quasi-locality that it's not just any crazy thing can happen where an observable sitting here, could be written in terms of stuff all over the place. There is this kind of version of locality where within a subregion, where a subregion on the boundary is dual to a certain subregion in the bulk, such that anything within that bulk region can be written in terms of the operators in that boundary region. Okay, the bulk region is called the entanglement wedge. Why is it a wedge? We'll see later, if I get to that part of the talk. Okay, so this formula is incredible. It has so many, it contains within it so much physics. It's taught us so much about quantum gravity. It's also taught us a lot about quantum field theory because you can turn around and use it to calculate entanglement entropies. One thing I'm not going into at all is that these entanglement entropies in quantum field theory are generally very, very hard to compute from first principles. And this gives you a very simple, if you're lucky enough to have a holographic dual, you just solve this minimal surface problem, like a classical plateau problem, and you're all set. So it has this magical feature. Here I'm more interested in what it tells us about quantum gravity. What it does is it beautifully geometrizes entanglement. So I'll show a bunch of examples of that. So first of all, we learned that the entropy has this UV divergence, so therefore this area should have a UV divergence, and it does. And that is reflected by the fact, and I didn't tell you this before, but actually the distances out near the boundary here are getting infinite. And so when you actually compute this area, you will find that it's actually divergent. And furthermore, the divergence matches perfectly the prediction from quantum field theory. I mean, you can see that it's going to be proportional to the area because you have the area here, again, terminology, the area here being the length of this curve. Okay. And it's going to be proportional to the length of that curve because the amount of surface, of RT surface near the boundary is proportional to the length of that curve. And the coefficients match and all that stuff. Okay, I told you that for a massive theory or a gap theory, you just have short range entanglement. Now the holographic dual of a gap theory has a wall in the bulk. So this is my boundary, and as you go away from the boundary, at some point space just ends. There's different ways for it to end. But no matter how it ends, what you see when you look for the RT surface is the RT surface will just end on that wall, and therefore making this thing larger and larger will not increase the entropy. Okay? Well, if you're in higher dimensions, this is my poor drawing skills. I just did the drawing for a one-dimensional boundary, but if you're in higher dimensions, then you will reproduce that formula I wrote before for when you have short-range entanglement. On the other hand, if you don't have a wall, then your boundary theory is conformal. It has long-range entanglement, and you reproduce that by the fact that the RT surface just keeps getting bigger and bigger. It reaches deeper and deeper into the bulk the larger your region is. And so, for example, that if you remember, C over 3 log L over epsilon was the prediction for a conformal field theory in one dimension. You reproduce that quantitatively. Okay. What about if you're at finite temperature? We have an extensive entropy there, proportional to the entropy density and proportional to the volume of A. And how do you reproduce that? Well, then you're going to have a horizon. Here I could have done it like I drew it before, where we have a localized black hole. Here I did it where we have a planar horizon, so an extended system that's at some non-zero temperature. And in the bulk, that's going to be reproduced by a planar black hole that has an event horizon that's a plane that's parallel to the boundary. And so then this RT surface is going to hug that horizon, and you're going to get a part of the entanglement entropy, which is proportional to the size of your region A. Okay, so everything works perfectly geometrically, you don't need a black hole. So here there is a horizon, which is providing some of the entropy, but in general, this Bekenstein-Hawking formula, as rewritten by Ryu and Takenagi, does not explicitly, the black hole is just a special case. And it's not a particularly special case. It's just one case out of many. So you don't need a black hole. Bekenstein-Hawking works. So in other words, the Bekenstein-Hawking formula was never really about horizons in the first place. It was never actually about black holes. Okay? Yeah? I think there might have been two questions in your question. So let me answer the second one first. So so Bekenstein-Hawking formula is the leading term in an expansion in powers of h bar or Newton's constant. And similarly, Ryu-Takayanagi is the first term in an expansion in powers of Newton's constant. On the quantum field theory side, that is an expansion in powers of 1 over n, where n is the number of fields. And so this guy is order n is proportional to the number of fields. And then you have corrections, which are order 1 over n, and so on. And I'm not talking about those. They are present, and they are, in certain cases, calculable. So for example, this question before about what happens if you're at low temperature and you don't have a black hole and you just have a gas of gravitons and you're bouncing around in the box, then the first term would be 0. There's no horizon, and there's no minimal surface. And then that entropy is given by the first subleading correction, which is order 1. So I think that was your second question.
Let me add a part to that question.
Okay.
Do the subleading match also?
Yeah, to the extent that you can compute, I mean, most of the time they're really impossible to calculate on the QFT side. But there are, if you work very hard and you're working in, for example, a one-dimensional conformal field theory where you can use all this extra symmetry and so on, then you can compute those corrections and you can match them. So yeah. Yeah. Any other questions? Yeah.
Yeah. So you showed us that in a quantum field theory, the leading term to the entanglement is essentially the area
Yeah.
over the cutoff.
Yeah.
Now, if I apply this to black holes, we're essentially saying that the proportionality factor C cube over h bar blah 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 is just a cutoff.
Okay, so
What is epsilon? What's the meaning of epsilon? Kind of weird.
so of course it was noticed a long time ago that this UV divergence looks the same as the Bekenstein-Hawking formula in the sense that if you take the black hole as a region of space and then you compute the entanglement entropy between the interior and the exterior, you will get this divergent term. That is not actually the same as the Bekenstein-Hawking formula. And the reason is that the epsilon is not the same. So there's a bit of a song and dance you have to do here. If you want to be careful about this entanglement entropy so what we're now talking about is the entanglement entropy in a quantum theory of gravity, okay, between fields inside and fields outside. You need to introduce a regulator, a UV cutoff to your quantum fields. That UV cutoff has to be larger than the Planck length. So you get the area over epsilon. It does not match because the Bekenstein-Hawking is the area over the Planck area. So it doesn't match. So in fact, what the thing you have computed is a correction or is a contribution to the Bekenstein-Hawking formula. It is not equal to the Bekenstein-Hawking formula. And you can study that and you can try to match it to computing in other ways, and there's that's a very interesting thing. It has to do with renormalization of Newton's constant and so on. So yeah, but it's not quite the same thing. Any other questions? Yeah.
So if I understood well, you said that whenever we have a mass, it's a wall. We have a finite temperature, it's horizon.
Yeah.
What happens if we have both at the same time?
So there will be a deconfining transition where below the deconfining transition, you just have a wall, and then you have a gas of gravitons which bounce around between the wall and the boundary. And above the transition, the wall basically gets eaten up by a black hole, and it looks like that bottom picture. And you wouldn't even know necessarily that the theory is confining. So if you just have a plasma, and all you know is that there's a plasma, you can't, it's not easy to tell whether that plasma is from a confining theory or a conformal theory. And in this case, it would be because basically the wall is like behind the horizon is essentially invisible. and it starts to look like any finite temperature system. Whereas if your theory is conformal and you put it on a plane, there's no phase transition. At any temperature, no matter how small, you have a horizon. There's no temperature, there's no phase transition because there's no scale in that system, so there's no temperature at which it could have a phase transition. Any other questions? Okay, so again, what I want to emphasize is how the Ryu-Takayanagi formula geometrizes entanglement, and it's more than just this phenomenology I said about quantum field theories. There's deeper facts or more general facts about quantum states and quantum information theory that are built into space-time geometry as revealed by Ryu-Takayanagi formula. And I'll just give a couple of examples. I see that I'm running out of time. So one is strong subadditivity. So this is a fundamental property of entanglement entropies. And you can see that it's automatically obeyed by Ryu-Takayanagi by a very simple argument. That if we look at if we have some regions A, B, and C, and here I'm just doing a cartoon sketch, so the proof that I give is valid for any number of dimensions, any topology, and A, B, and C don't have to be sitting next to each other. That's just what makes the pictures the prettiest. So, but anyway, so if I have my left-hand side, I have A, B, and BC. So AB is going to have some RT surface like this. BC is going to have some RT surface like this. And then without changing the area, I can just reconnect them. So I get some surface for B, some surface for ABC. They're not minimal surfaces, but by definition, they're larger than minimal surfaces. And so we get this inequality. And so you're done. So it's sort of built, very much built in this very simple way. There's a whole set of other properties. So in fact, every property that is known to hold for entanglement entropies holds for the RT formula. Okay, I'm going to skip this, but there's a whole bunch of properties of entanglement wedges that are necessary for the consistency of this picture. I said that the entanglement wedge is the dual to the QFT within the region. So that means it has to satisfy certain properties having to do with what happens if you take the complement, what happens if you take a subregion, what happens if you take two regions, and so on. And that leads directly to a link. Essentially, the boundary can be thought of as a quantum error correcting code that encodes the bulk in a very precise sense. My title has the term time, space-time, but I have not talked about time. And actually, it's way more interesting. So yeah, let me just, sorry for doing that. Okay, so all of these are, it's amazing how it fits together. They're also very simple things. So something like that SSA proof is very simple, and all of these things are very simple. So somehow what's missing, although it's neat that it works, is like the physics of the bulk. I mean, it's a quantum gravity theory. Like, where do you see that? Is there Einstein's equations? Like what, and that actually comes into play when you include the time direction. And you try to reproduce all of this stuff, prove strong subadditivity, prove entanglement wedge nesting in a time-dependent situation. So now all of this was for static states. And that's where things get very interesting and where I also just run out of time. So you have to change your formula. Because now your extremal surface, your RT surface, is living in space-time, and you end up with a codimension 2 surface, and you have to prove properties of that codimension 2 surface and its area. And those are proper GR theorems. They're very similar to like Hawking's area theorem or Penrose's singularity theorem in terms of the ingredients. You use the Einstein equation, you use some energy condition, and you prove these theorems, which again are necessary for the consistency of this formula. Okay, and so this is actually where I live right now, is in this space of connecting GR to quantum information theory. Okay, so proving GR theorems that tell you something about how space-time encodes quantum information. So there's a direct, so again, there's this incredible match between, on the one hand, general relativity, and on the other hand, quantum information theory, and they just match absolutely perfectly. This is the thing that I find absolutely incredible, okay? You can go the other, because all of these properties depend, as I said, you use the Einstein equation to prove them, so if you're smart enough, you can go the other way and actually derive the Einstein equation from these properties, assuming this RT formula, okay? So that is something that has been done where you can assume this entropy formula and you know things about entanglement, and you can derive the Einstein equation within, at least at a perturbative level near anti-de Sitter space. There's a whole fascinating subject about these 1/n corrections, which are quantum effects in the bulk, and how you get out the so-called page curve, and that's very interesting. Although to me, I mean, yeah, somehow this is, okay, this is brilliant work. I mean, this is incredible work. I'm not trying to in any way denigrate or say that this was obvious, but there's a level at which I feel like this kind of had to work, whereas this business of GR to me, what blows my mind more is the fact that the classical general relativity knows quantum information theory. The fact that quantum gravity knows quantum information it's a quantum theory. The fact that classical general relativity knows and encodes quantum information theory, I find more mind-blowing. Okay, so what are we supposed to learn? So somehow classical space-time is a representation of entanglement. You can think of it as a coarse-grained representation because it's only getting that leading term. Thanks for that question about corrections. So in some sense, it's like a hydro description, if you want, of entanglement. But the point is that the entanglement is in there. So instead of gravity being hard to quantize, gravity is already quantum. Classical gravity is already a quantum theory in some sense. It already encodes quantum mechanics in it. You can't not quantize gravity. Okay? So then that leads us back to this question about whether you should set Newton's constant to 1. In other words, which is fundamental? Is it the strings or is it the areas? And I mean, obviously, this is the kind of question that doesn't have a sharp answer because these are just two different viewpoints on the same thing. You can take the point of view that the strings are fundamental, or you can take the point of view that this hydro description, sorry, not that the hydro description is fundamental, but that the entanglement underneath it is fundamental. And then you have excitations, and the excitations, which are things like gravitons, can take the form of strings. Okay? Okay, so that's my boring answer to this question. But Yosef will be able to explain to everybody why the answer, which one was it? I forgot which one. It was yes. You were in favor of it. Okay. And then, of course, the mandatory at the end of the talk list of open questions, which obviously here is vast. So it's like we've noticed this phenomenon that space-time encodes quantum mechanics, but we don't have a first principles understanding from which what you want is a description from which these facts I've told you are just kind of obvious, that they had to be true. And we're not at that stage. We're still at the stage where these facts are mysterious and amazing. Okay? And that is even in this case where we have this ADS boundary, which is not the case for our world. Instead, we have like a beginning of the universe in the Big Bang, possibly. So it's just, yeah, we're just scratching the surface here. And that's it. Thank you so much.
Thank you for a very, very nice talk. Are there more questions?
Yeah, I'm bugged by a little paradox. If the black hole entropy is an entanglement entropy, because SA equals SB, the entropy of the universe, I would like to think of it as an entropy of entanglement with the black hole. And it should be of the same order of magnitude, but you showed us it's much smaller. So is something missing?
Okay, so I did a trick where I doubled the universe, and in order to purify that, in order to turn that black hole entropy into a entanglement entropy, a priori it's not physically that's like a theorist trick. A priori it's not physically an entanglement entropy. It's more it's a statistical mechanical entropy which arises from the fact that the black hole has many microstates and I've coarse-grained. Okay, so you can always do this. You have a box of gas, it has some entropy. As a theorist, you can imagine a second box of gas and they're entangled, and all of that entropy was entanglement entropy. Okay, so the black holes in our universe, I mean, is there a second universe and it's all entanglement entropy? I mean, it's not ruled out, but there's also no particular reason to believe that that second universe really exists. It's much easier to imagine that since those black holes were presumably formed by collapse and matter coming in and so on, that they have some, particular microstate that they are in. Of course, we can't possibly know what it is or describe it, so we give this coarse-grained description, the same as we do for the air in this room. The air in this room is in some microstate, but we don't know or really care what microstate it's in, so we give it this coarse-grained description. So I don't know, is that kind of answering your...
Well, I'm still disturbed by the fact there is so much entropy in the black holes, but that's okay.
It's because it's mining the quantum gravity. Like, it's a phenomenon that actually sees the Planck length. After denigrating this idea of the Planck length as being meaningless, now I'm saying that it's fundamental, and so it's the fact that these degrees of freedom which are intrinsic to space-time itself have become activated only happens in a black hole. They don't happen in a neutron star or in the CMB photons. That's what gives you this huge number.
That's the question I was also thinking about. But this is very optimistic because these black holes were not here at the beginning of the universe, so they are created. So our entropy is decreasing all the time. So that explains probably why we're getting more and more clever.
Are we? So the entropy of the universe is definitely increasing, and almost all of the increase is due to black holes merging and eating up stars and growing, and generally growing. In the very, very distant future, if there's no big crunch, if the universe continues to expand forever, in the very distant future, it's going to go through phases where one phase is going to be that all the matter will be in black holes. There will be only black holes. And then much, much later, those black holes will evaporate and there will be only photons. So when a black hole evaporates by Hawking radiation, the entropy again increases as it has to. The number of photons is, of course, very large. That's all that would be left. That would be the final heat death of the universe. So in other words, the final heat death of the universe will not be black holes, although they have a very large entropy. It will actually be photons and gravitons that are emitted by those black holes. Unless the universe crunches. We don't really know. Yeah.
Why should the black holes in the very long time should evaporate only through photons?
They evaporate mostly through massless particles. I guess there will be they might emit like a very small number of like protons and electrons. Actually, okay, I haven't thought about this in detail, but by far most of the Hawking radiation is going to be in gravitons and photons. Yeah, that's why it takes like a ridiculously long time, like 10 to the 10 to the 10 to the whatever, for like the supermassive black hole in M87 to evaporate takes in. So that's why if the universe big crunches, then all of this is irrelevant, because it'll crunch long before any of this evaporation happens. But in a scenario where the universe just keeps expanding forever, it will eventually evaporate.
Okay, so talking about the end of the universe is a good point to end the talk. We will not go to the rotonde today because I think there is a flood or something. So we will actually go to the canteen. So if you want to join, you're all welcome, and we can continue the discussion there. So thanks again.